Physics can be dangerous. We're not always solving equations for X. Sometimes we solve them for oops.
Oops.
The world learned this the hard way with the development of the atomic bomb. Now NATO and several physicists too are saying that we need safety rules for quantum technologies because they can be dangerous. Really? Yes, really. And they do have a point. Earlier this year, NATO put forward a quantum technology strategy, according to which quantum technologies have potentially revolutionary and disruptive implications, which can degrade the alliance's ability to deter and defend. Quantum technologies are therefore an element of strategic competition. They say that NATO needs to become a quantum-ready alliance. One of the desirable outcomes, they say, is that allies have cooperated in the development of quantum technologies with a view to maintain NATO's technological edge and allies' abilities in the field. A few months later, New Scientist reported that multiple nations, including the UK, France and Canada, have suddenly introduced almost identical export restrictions on quantum computers that have more than 34 qubits. I'm sure this is a complete coincidence. This development upsets some researchers because they see it as a hindrance to research. There is no calculation you can do with a 34-qubit quantum computer that couldn't be done better, cheaper and more easily otherwise, but one can speculate that the reason for the export restriction might be to limit the spread of technology before it can be used for evil purposes. And yes, there are such evil purposes. The most discussed risk for quantum computers is that they'd be used to crack cryptographic protocols, which have been used to secure national secrets for decades. So if any nation spied on another and pocketed encoded files, these might suddenly become readable. But this isn't the only reason NATO might worry. There are other ways quantum technologies can be abused. For example, one of the potential applications of quantum computers that has attracted the most interest is calculating the properties of molecules without having to synthesize them. This could become extremely useful for material design or drug development, but it could also become useful for the development of better chemical or biological weapons. It's not just quantum computers that might be useful in this, also various technologies for quantum sensing that make it easier to measure the properties of such materials. Then there is the idea of a quantum radar that enhances the effectiveness of radar by using entangled light. You can see how militaries might get worried if someone has a better radar than they have. Then there is the quantum compass. That's a supersensitive accelerometer, so it measures acceleration. This is useful because if you know exactly how much you accelerated and for how long, you can calculate your exact path. And if you know the starting point, this means you can calculate your exact position entirely without GPS. So this gives you protection if the enemy is trying to jam your systems. The British Navy has been testing such a device. And then there's the general issue of getting an edge in certain computations, like military logistics. In a recent commentary in Nature, a group of scientists drew attention to the security problem for quantum tech. They write about what you expect for a Nature comment, something about developing ethical governance and multilateral collaboration and oversight, and ensuring that securitarization is justified and balanced, because if there's one thing we all trust to keep things under control, it's committees. So what are we to make of this? Is this a real threat? When it comes to technology that's relevant to the military, there's always the question of how much information they're sitting on that we don't have. I'm pretty confident that quantum computers aren't anywhere near practical applications. I say this because there are probably hundreds of labs all over the world working on it, and it's highly unlikely that the military of any country would do better than all of them combined. That said, I'm not so sure about other technologies that haven't been widely explored. The thing with the quantum radar strikes me as a case where quantum effects will give you a very small advantage for a lot of effort, and while that's possible, it won't make much sense in practice. The quantum compass is a real thing, and I actually think it might be one of the best applications of quantum tech yet. I'm somewhat surprised, honestly, there isn't more work on this. Maybe someone just needs to market it as the Quantum Pathfinder Pro Max. So I think we shouldn't just brush off worries that quantum tech might be used for unethical purposes. However, at the moment, quantum tech is so impractical to use and so expensive that there are few actors in the game. And in any case, the world has better things to worry about, like what video to watch next, so don't forget to subscribe and let me know in the comments what you want me to talk about. For more than half of a century, progress has been closely linked to Moore's law, giving us a constant increase in computing power. Then, 2 years ago, Jensen Huang, the CEO of NVIDIA, one of the world's leading computer companies, declared Moore's law dead. But now he hasn't only changed his mind, he thinks that we'll see a hyper-Moore's law.
The way people think about Moore's law, which is 2x every couple of years, we're going to be on some kind of a hyper Moore's law curve. And I fully hope that we continue to do that.
Before we look at what he meant with that, a big thank you to all our supporters on Patreon, especially those of you in Tier 4 and higher. Your help is greatly appreciated. And you too can help us on Patreon or by joining this channel right here on YouTube. Right, so now about Moore's law. It's been with us since 1965, when Gordon Moore, one of the brains behind Intel, noticed that the number of transistors on a microchip was doubling roughly every 2 years at a minimal increase of cost. Moore's law has largely held true until a few years ago, which was when Huang declared Moore's law dead. This is primarily because transistor sizes are hitting physical limits. They're now in the nanometer range and becoming increasingly more difficult to cool. Last year, I made a video about what new technologies are in the works that could continue Moore's law. That could be photonic computing, carbon nanotubes, spintronics, or quantum dots. But none of those are ready for mass production yet. And whatever will happen to the supposedly impending artificial intelligence explosion if Moore's law fails us? So what NVIDIA has been doing instead is optimizing the relation between software and hardware. Huang calls this co-design. The first example of this was the distinction between CPU, that are the general processing units of a computer, and GPU, the graphics processing units, especially designed for, graphics. NVIDIA now also has GPUs that are especially designed for matrix operations, that are used a lot in the training of neural networks, that are used for the currently most common type of artificial intelligence. These GPUs have extra logical circuits called tensor cores. But besides training neural nets, there are other reasons for why you might want to choose suitable hardware based on the software. For example, the current state-of-the-art precision for calculations is 64 bits. But maybe you don't need 64 bits to calculate what ad goes on top of the page, which seems to be most of what they calculate at Google these days. So you might want to have a system that adapts the calculation depth depending on the problem from 64 to 32 or even 4 bits. This doesn't just speed up calculations, it also saves energy. This is why this co-design of software and hardware can both get you faster calculations and save energy. And that's what Huang refers to as hyper-Moore's law, a performance increase that outpaces Moore's doubling law.
Our hope is that we could double or triple performance every year at scale, not at chip, at scale. And to be able to, therefore, drive the cost down by a factor of 2 or 3, drive the energy down by a factor of 2 or 3 every single year. When you do that every single year, when you double or triple every year, in just a few years, it adds up. So it compounds really, really aggressively.
And NVIDIA is on the way already. Earlier this year, they released the Blackwell platform that they say speeds up the training of large language models by a factor of 30 and that of simulations by more than 20 times. That's what they say. So far, there haven't been any independent tests. Instead, customers are reporting that the chips are overheating. The key feature of the new platform is the improved linking between GPUs that allows to distribute data processing in the most optimal way. They do this with a system that NVIDIA calls NVLink.
This is NVLink, and it goes across the entire back spine of a rack of GPUs. And these GPUs are all connected from the top to the bottom using NVLink, driving these incredible SerDes, the world's longest driving SerDes for copper. And it connects all of these GPUs together.
This platform is targeted primarily at enterprise-level and research-oriented applications, such as AI companies, supercomputing facilities, and large-scale scientific projects. But Downwind will probably all get something out of it. Did you know that I have a free weekly newsletter with some extra news items? You can sign up at sabinehossenfelder.com/newsletter. That said, a lot of companies are now also developing chips that are especially suitable for AI training. They're called neural processing units, NPUs for short. Interestingly enough, this is something which NVIDIA is not doing, but big companies like Intel, AMS, and Samsung are banking on NPUs, and some dedicated startups are working on that too. These NPUs could become one of the main rivals to NVIDIA. By the way, when I said that Moore's law kept the production cost roughly stable despite increases in computing power, that's the production cost after development. The necessary investments into research and development have increased by roughly a factor 20 since the 1960s. And that's one of the examples of how we have to make more and more effort in research that I just talked about the other day. And when NVIDIA is done with that co-design, maybe someone can go and figure out how to get my phone to communicate with the printer. That'd be great. A month ago, I told you about Stephen Wolfram's attempt to develop a theory of everything based on hypergraphs. And just the other day, I learned from New Scientist that if he's right, it'd imply a characteristic change in the emission of supermassive black holes that could be observable. That'd be very interesting if true. So let's have a look. In my recent video about Wolfram's hypergraphs, I mentioned that most of the recent work on this seems to have been done by a young mathematician by the name of Jonathan Gorar. I didn't know, though, that the two seem to not be on the best of terms, as Gorar mentioned on Twitter that spending the last 5 years watching Stephen take sole credit for ideas, insights, developments, and discoveries that were the products of our collaboration has been a uniquely exhausting experience. This new work also comes from Jonathan Gorar and is based on hypergraphs, but it doesn't seem to directly involve Stephen Wolfram. As a brief recap, a hypergraph is a set of graphs or networks that describe space-time, not just space, but space-time. They have a finite resolution that on the one hand can reproduce Einstein's theories to good accuracy. On the other hand, it can avoid the troubles that Einstein's theories have on the shortest distance scales where singularities can form. This way, the hypergraphs might one day also help to recombine general relativity with quantum physics. Discretizing spacetime has of course been tried before, but most attempts have run into conflict with observations quickly. This is because in Einstein's theory, you just can't have discrete chunks of a fixed volume of space. This is because of length contraction. Something that's very big for one observer will be very small for another one, and volumes of space can change. So the idea of having discrete space is itself incompatible with Einstein's theories. Hypergraphs circumvent this problem because they're treating space and time together as one entity and have deviations at small volumes of space-time, not volumes of space, but space-time. If length contracts, then time dilates, but the product remains the same. So this doesn't result in any obvious problems with the symmetries of Einstein's theories. Gorar now used these hypergraphs to describe what happens if a black hole accretes matter. The matter will spiral into the hole and heat up dramatically along the way. This releases a lot of radiation. We can observe this radiation from many supermassive black holes in the middles of big galaxies. In a paper from February, Gorar uses fluid dynamics to describe the accretion of matter onto black holes and says that the amount of energy that is emitted depends on how dense the hypergraphs are. You see this blue holy stuff here? That's a hypergraph which replaces the continuous spacetime. The less dense the graph, the higher the deviations from Einstein's theory. In the paper, he doesn't quantify it, but just somewhat vaguely writes that these results provide tentative evidence that there may exist astrophysically observable possible effects of the underlying discreteness of space-time arising within certain quantum gravity models. Then, a few weeks ago, he leaked on X Twitter some preliminary results, according to which preliminary simulations suggest that this could result in a boost in jet luminosity, assuming approximately Planck scale discreteness, of around 2 to 3 times over the predictions of classical general relativity. Big if true, as they say, because that might mean that we could be closer to finding evidence for the quantization of gravity than we thought. However, the reaction of physicists to this claim was deep skepticism. Alessandro Strumia writes, "The physics is low-energy junk falling in a hole. Effects of Planck-scale physics should be tiny." And Ted Jacobson, quoted in New Scientist, says likewise, "I don't see how this idea can make sense. Any viable discreteness would be at a very small scale compared to the scale relevant for the physics of accretion." The reason they're saying this is that usually you expect deviations from Einstein's theories at a strong space-time curvature or at extremely high energy densities respectively. I know it's somewhat counterintuitive, but the space-time curvature near black holes is actually very small, and the energies that are involved there are also small, at least compared to the ones where you expect deviations due to quantum gravity somewhere at the Planck scale. That said, I think this criticism ignores the exact way that hypergraphs implement the space-time discreteness. As Gorar writes, the deviations come from the way that hypergraphs suddenly increase the ratio of the number of possible paths that cross into the black hole horizon because there just aren't any other paths. It adds to this that fluid dynamics is fundamentally chaotic. It can amplify effects from short to large distances. This is the famous butterfly effect. So I think the case isn't all that clear-cut, and it's worth to wait and see what Gorar is up to. Did you know that I have a free weekly newsletter with some extra news items? You can sign up at sabinehossenfelder.com/newsletter. So what are we to make out of this prediction that supermassive black holes might test quantum gravity? Honestly, I strongly doubt that what Gorar says is correct. I actually find this interesting for reasons that have nothing to do with quantum gravity. It's that Gorar is clearly a mathematician by heart. So are Stephen Wolfram and Eric Weinstein and Peter Voigt. But physics isn't maths! Mathematicians usually know nothing about theory development, and seeing them do physics is like watching a rabbit hop into a snake pit. You know it's not going to end well, but you just can't look away, so don't forget to subscribe. If you trace back your genetic family line a few billion years, it doesn't only join with mine, it joins with those of all known animals and plants and bacteria to one organism, Luca, the last universal common ancestor. Scientists believe that every living thing on Earth descends from Luca. It's just taken us about 4 billion years to learn speaking English. But a recent study delivered quite a surprise. It's found that Luca was much more complex than previously thought, and that raises a lot of questions about the origin of life. Let's have a look. Luca is a hypothesis, but a well-motivated one. It's based on the observation that all living beings on Earth are built up in similar ways. They all have similar molecular and cellular features, such as the genetic code, ribosomes, and metabolic pathways like the way we generate energy from sugar. And to the extent that we can test this with fossils, it's also the case well back in time. Scientists think that Luca was not the origin of life itself. There were likely simpler self-reproducing structures before that, though it somewhat depends on what you mean by life. If life means arguing about the Oxford comma, I don't think Luca was quite there yet. But just exactly what sort of organism Luca was, no one really knew. This is where the new study comes in. These researchers did a sophisticated genomic analysis of pretty much everything they could get their hands on to identify the genes which all known organisms have in common and which therefore likely originated in Luca. They found a whopping 2,657 of them, much more than any previous study. We mostly know what these genes are good for because we know what proteins they synthesize. The genes seem to indicate that Luca was good at using hydrogen gas as an energy source. This is very interesting because it tells us something about the environment in which Luca must have lived. Hydrogen gas can be created near hydrothermal vents, which are one of the suspected places for life to have emerged. A hydrothermal vent is a place on the seafloor where water that has been warmed from geothermal heat bubbles up. The warm water can react with some of the minerals in the rocks, which creates hydrogen gas. Luca might have lived there. This fits very well with what researchers have been speculating about the origin of life already, but much more interesting is the part that doesn't fit. That part had it that when Luca lived about 4.2 billion years ago, organisms were incredibly basic. But this is not what the new study found. Even though this study might have missed some genes, it gives us a minimal set of what Luca must have contained. They estimate Luca's genome size to be about 2.75 million base pairs of DNA. Just for comparison, human DNA has a little over 3 billion base pairs and onions about 13 billion. Yes, that's right, onions. Those smug vegetables have more genes than we do. If you've ever cried cutting one, maybe they deserved it. The fact that the genome size doesn't predict an organism's complexity is one of the big open problems in genetics. So if you're getting tired of reinventing quantum mechanics, maybe give this one a try. With all these genes that the researchers have identified for Luca, they were able to generate sort of a flowchart of its metabolic pathways, and it's way more complex than anyone thought. You see it in this figure. Yes, that looks like an old Windows screensaver had a baby with biochemistry, but maybe Bill Gates knows something we don't. They write in the paper, the result is a picture of a cellular organism that was prokaryote grade rather than progenotic, and that probably existed as a component of an ecosystem. This basically means it's more complex than they thought. Prokaryotes are organisms that still live today. For example, many types of bacteria like E. coli. They're typically 1 to 10 micrometers in size and have a cell wall, but no nucleus that holds the DNA. Instead, the DNA floats freely on the inside. The reason this is relevant is that we know roughly when Luca existed, and there wasn't a lot of time for it to grow to that complexity, because just 500 million years earlier, Earth was quite literally a hot mess. So this study means that either life can form much easier and faster than we thought, or it was seeded by some sample from outer space. The former fits together well with another study that I talked about in an earlier video, which argued that if you have sufficiently many molecules, you'll pretty much inevitably get autocatalytic cycles that are molecular reactions that sustain themselves and that are believed to be a precursor to self-reproduction, which itself is a precursor to life. I find this incredibly interesting because it supports my confirmation bias that extraterrestrial life isn't rare but quite common. Or life on Earth actually came from elsewhere, and now the aliens are sitting there thinking, we sent them our best microbe, and all we got was this lousy YouTube video. Thanks for watching. See you tomorrow.